Hello everyone and welcome to yet another Calculus 1 video. The topic for this video is antidifferentiation and it corresponds pretty well to Larson Calculus section 4.1. So in this video I will be going over the definition and representations of antiderivatives, why the plus c, that'll make more sense in a little bit. We have some basic integration rules, then we'll have examples on how to use those basic integration rules. We will have initial condition problems toward the end, and then physics. Yep, physics is back. All right, let's take a look at antidifferentiation. What is an antiderivative? Well, a function, capital F, is an antiderivative of little f on an interval I when capital F prime of x equals little f of x for all x in that interval I. So it's basically what's going to happen is we're going to be given some function and we're trying to figure out what function could we take the derivative of to get this function. That's what function could we take the derivative of to get our function? So we are, in fact, doing the exact opposite of finding a derivative. This will make more sense when you see some examples. So as far as the representations are concerned, if the capital F is an antiderivative of f on an interval I, then g is also an antiderivative of f on that interval I, if and only if g is of the form g equals f plus some constant. So there's the plus c for all x in that interval I where c is a constant. So what you'll come to find is that functions have families of antiderivatives, and it all depends on us not knowing what c is. So how does this work? Let's take a look at that on the next slide. So here I have 4 different functions listed out. You can see them here. F, G, H, and K. The problem here is all of these, if you take the derivative, give you a derivative that looks like this. 3x squared. Remember how the derivative works? We have to, for any variable with a power, we can just use the power rule, bring the power to the front, that's why it's 3 is in the front, subtract 1 from the power, now it's 2. The derivative of any constant is 0. Yeah, pi to the 14th power, that's a number raised to another number, that is a constant. All of this is a constant, all of this is a constant. The antiderivative process, though, tells us, hey, we're trying to go backward. The antiderivative wants us to go this way. So if we know this function 3x squared, which function are we supposed to get? Well, we have no idea. We have no clue. That's why, since we can't specify what constant it is, we have an entire family that we have to think of. And it's pretty easy for us to represent that. We just don't pick a specific constant. We just add c instead. C could stand for any constant. Toward the end of this video, we will go through some initial condition problems where you know a little bit about the original function and you can nail down what the c value is supposed to be. But if you don't know anything about the original function, you just have to write plus c. So that's why in the last definitions on the last slide, it didn't say the antiderivative, it says an antiderivative, because there are multiple antiderivatives that could happen. As far as the notation is concerned, we want to be able to find the capital function from the lower function. So we start here. Remember we were having differentials not that long ago. And so if we had the dy dx being the derivative, and I missed a prime here, this would be f prime of x. We could multiply both sides by dx, as I did here. So let me write that in actually. So we could multiply by dx, and we would end up with this equation here. Then we can introduce the new notation. We can introduce the integration notation. So here, this little bar here and this little s bar here. And take my word for it right now. This side of the equation becomes y. So let's see here, this would become y equals the integral of f prime of x dx. So what we're getting at here is this was the derivative of y dy with respect to x. We can undo the derivative by using this notation. We say finding the antiderivative of f prime of x with respect to x. So this here is what we call the integrand, the function or the expression that we are trying to find the antiderivative for, and the variable after the d is the variable of integration. So we would say, again, the antiderivative of f prime of x dx with respect to x. One other really quick fact about this is the antiderivative and the derivative are inverse operations. So it doesn't matter the order with which we do this. I could have also written here that y would be equal to the antiderivative of f of x dx prime, and these two things are equivalent. So that's something that's pretty cool about that. It's kind of like if you square x and then square root it, or if you square root x and then square it, they're pretty much the same thing. Not exactly the same thing, but they're pretty much the same thing. At the end, you always end up with x. So something like this, the integral and the derivative are inverse operations and will undo each other. On this slide, we have some basic antidifferentiation / integration rules. So first, we have the antiderivative for a constant with respect to x. That constant just ends up being multiplied by the variable, and then we would have to add that constant of integration there because we don't know which function it's supposed to be. That c could represent one of an infinite number of numbers, which is just a really weird thing to think about. So a really quick example, if I had the antiderivative of negative 7 dq, then this would be negative 7q because the variable has to match. So the q would match here, plus c. So there's just a really quick example. The rest of these should feel pretty familiar from when we did them with derivatives. Here, the second equation, we have a constant being multiplied to the function, and if we take the antiderivative of all of this, it's the same as finding the antiderivative of the function and then multiplying by the constant afterward. We did that multiple times with derivatives. Next, we have the sum and difference rule. We can either add the two or subtract the two functions and then find the antiderivative, or we can find the antiderivative of each function individually and then add or subtract them at the end. I'm going to come back to this one in a second. This one is probably going to be the most important one here. Then we have antiderivatives of trig functions. So the antiderivative of cosine with respect to x is sine of x plus c. The antiderivative of sine of x dx with respect to x is negative cosine x plus c. And the way you can think of these two down here is that if you took the derivative of these, you should get what the integrand is over here. So if I take the derivative of negative cosine, we know that cosine, the derivative, should be negative sine, and a negative should be a positive sine. Check that out. We got what was supposed to be here. So if you take the derivative of all these answers over here, like this or these or even this, you should just end up with what was inside the integral to begin with. So this one, this is a super important rule here. This is the basis for most integration that we will do. This is the power rule. And this is the power rule for integration. And it exactly undoes the power rule for differentiation. Again, these are inverse operations. So for a derivative, way down here, you remember if we had a derivative of some variable raised to a power, we brought the power to the front, then we subtracted 1 from the power. What happens here with the antiderivative of all of this is that you have to first add 1 to the power, then divide by the new power, which is exactly the opposite. So here we're subtracting 1 from the exponent, here we're adding 1 to the exponent, here we're multiplying by what used to be there, here we're dividing by what's there now. It's exactly in reverse. So you can see I have two different expressions here. This one, oops, there we go, and this one. So there are a couple different ways to explain this, this power rule. The power rule, you could say add 1 to the exponent, divide by the new exponent plus c. And that works out until the exponent becomes a fraction. And then it just really breaks down. Students forget to take the reciprocal of the exponent. So I tend to this explanation or this writing of it. You can add 1 to the exponent, and this is multiplying by the reciprocal of this exponent. So let me get that here. This is the reciprocal of the new exponent. This is how I will do it, because when we end up having rational exponents, this is much, much easier to find. There are just 4 more antidifferentiation rules on the next slide. They're all trig-based. Let's do it. Here we have some basic rules. Continue all of the trig rules coming back. So we have the antiderivative of secant squared x with respect to x is tangent of x plus c. Secant tangent with respect to x is secant of x plus c. Cosecant squared of x with respect to x is negative cotangent. These are all very, very familiar. So, again, I'm just going to pick one of these. Let's pick this one. If I have this here, antiderivative cosecant squared x dx equals negative cotangent of x plus c. If I really want to see how this works, I very well could take the derivative of both sides. So let me get a different color here. Let's say the derivative with respect to x of all of this, and the derivative with respect to x of all of this. Since the derivative and an antiderivative undo each other, this and this, because the integral sign and the dx are like one piece of notation, we are just going to be left with cosecant squared x on this side. Next, I'm just going to leave this side alone as d dx negative cotangent x. The derivative of a constant is 0, so we don't even have to include that here. We can find the derivative of the constant. It's 0. Ta-da, plus 0. Now the only thing that almost makes this look like a formula you know for derivatives is this minus sign. Well, luckily for us, we can move it to the front of this derivative, and then we can divide both sides to get negative cosecant squared x equals the derivative of cotangent x, which is exactly what you learned during the derivative units. So if we went backward and found the integral of both sides here, the antiderivative of both sides, we would get this plus c back. We would leave the integral or the antidifferentiation notation here, and there we go. We have it. So all of these should not be too hard to understand. It's just that the notation is different. That being said, in order for you to get used to this new notation of antidifferentiating or integrating, let's look at some examples. All right, on this slide of examples, we have examples of integration. And in example 1, we're going to solve for y. And you take a look at this equation, and you're asking yourself, where's y? I don't have any y's. Well, this is like the what we call a differential equation, because we have the differential of y and the differential of x. And if we just multiply both sides by the differential of x, we can see that we end up with this equation, dy equals 2x to the negative third power dx. Now here's the key. We are going to take the antiderivative of both sides. So here and here. Now hiding in here in front of the dy is a 1. And the very first rule said this: if we take the antiderivative of 1 with respect to y, it's almost like we can just magically put that variable there. So this would be 1y equals, now here we have the antiderivative of 2x to the negative third power dx. So when we find the antiderivative here, we will use the power rule. And the power rule states, and we're also going to use the constant multiple rule. So this 2 will still be here. And we will multiply this by, what do we get? We add 1 to the exponent. So this will become x to the negative 2 power. And then I can represent this one of two ways. The first way is I could divide by the new exponent, and we could do that. I tend to do this. I could say we can multiply by the reciprocal of the new exponent. So the new exponent is negative 2. The reciprocal of that would be negative 1/2. Plus c. From here, then all I have to do is simplify this multiplication here. 2 times negative 1/2 sure is just negative 1. X to the negative 2 power plus c equals, we don't have to write this 1 here, so on the left side we can just say it's y. Now the very last thing, of course, as with all the derivatives we've done, we have to push this to the bottom of the fraction to get rid of the negative exponent. And we have the answer here, y equals negative 1 over x squared plus c. Now, you may have a question like, hey, why did you add plus c on this side, but not on this side? Well, technically there would have been a plus c here, and it would have been just another constant. We'll call it c sub 1. But if I would have moved this c sub 1 over here and combined it with this c, we still would have had a constant. Right? A constant minus a constant is still a constant. So we generally just push all of the constants into one term, just one giant plus c at the end of it. All right, so same thing here. For example 2, we can solve for y. Well, that means first we need to multiply by dt. Then we need to find the antiderivative of each side, and again, the left side will turn into y. The right side this time will turn into 5t, because this variable, whatever we're finding the antiderivative with respect to, has to be the variable that shows up in the expression on that side. And then, of course, our plus c at the end. There we go. All right, let's move on to the next slide. All right, on this slide we have a couple more examples. You can see we have example 3 and example 4. And what is going on in the background, we had a sum and difference rule back in our list of basic integration or basic antidifferentiation rules. And what that really tells us is that we can find the antiderivative for 9x to the 8th power dx. We can subtract the antiderivative of 2x dx, and we can subtract the antiderivative of 6 dx. So we can separate all of these out like this. We can use the constant multiple rule to say move this 9 here out of the integration. We can move this 2 here out of this integration. So our equation looks like this. Then we can use the power rule for this term and this term, and we can use the antiderivative of a constant for this term to get something like this. The 9 and the 2 are still coming along for the ride. So let's see here. What would we get? This would be minus. So here, for this antiderivative, we would add 1 to the exponent here. So I would have x to the 9th power. And to that, I would multiply by the reciprocal of the new power, in this case 1 over 9. The next one, I just have to add 1 to the power of this x squared, and I would multiply that by the reciprocal of the new power. The reciprocal of 2 is 1/2, and luckily for this last one, 6, we can just write minus 6x. So that's nice. Oh yeah, and then super important, plus c. That is what most students will forget, and that is what will cost the students most points on an exam. So now all we have to do is simplify. 9 times 1/9 here is 1. So we were just left with x to the 9th power, minus 2 times 1/2 is 1, x squared, minus 6x plus c. Now eventually, if you don't see it already, we won't have to use all of these little rules like the sum and difference rule to separate these 3 terms into their own antiderivatives. We won't have to use the constant multiple rule. We can just jump from here to here. And I'm going to do that with this example here. So you can see here we have the antiderivative of 4t minus 1, the quantity squared, with respect to t. We cannot, in its current form, find the antiderivative for this expression. What we have to do instead is we have to actually multiply this out. So when you multiply 4t minus 1 times another 4t minus 1, you'll get 16t squared minus 8t plus 1. Now, I mentioned just a few seconds ago that I'm not going to go through all these steps again. What we can do is once we have all of our terms, we can just jump right into antidifferentiating here. So I have 16 times, the only thing we're antidifferentiating is the variable at this point. So I will add 1 to the exponent and then multiply by the reciprocal of the new power, So I will subtract 8. And for this variable, I will add 1 to the exponent and multiply by the reciprocal of the new power. This last one here, luckily we can just write plus t. Right? The antiderivative of 1 is t, and at the end we'll have a plus c. So now we can just go through and multiply some constants together, like negative 8 times 1/2 is just going to be negative 4, and 16 times 1/3 is just going to be 16 over 3, right? We can't simplify that. So this will be 16 over 3 t cubed minus 4 t squared plus t plus c. So there's our answer here, without needing to write out these steps for the sum and difference rule and the constant multiple rule. And absolutely work your antiderivatives or your integrals, your indefinite integrals, out like this. This is much faster. There's less of a place for you to mess up, I think, than doing all this. One last thing that I want to mention here, something I kind of mentioned on the last slide as well, is that we turned one expression, one antiderivative, into 3 antiderivatives. This here, 1, 2, 3. And yes, technically, each one of these antiderivatives would give you a plus c. So this one right here would have had a plus c. This one right here would have had a plus c. This one right here would have had a plus c. I'm going to call them 1, 2, and 3. But instead of writing a plus c for every single term, again, constants combine to a constant. So we just put one big plus c at the end. You should only ever have 1 plus c in your indefinite integrals. Before we get to the next couple examples, I just want to point out something else really quickly here. If you find the derivative of this function, whereas you bring the power to the front and subtract 1 from the exponent, if you multiply this by 3, you'll get 16. If you subtract 1 from 3 in the exponent, you'll get 2. If you multiply negative 4 by 2, you'll get negative 8. If you subtract 1 from this exponent, you'll get 1. If you take the derivative of t, you get 1. So you should be able to find the derivative of this function. Oh, and the derivative of a constant is 0. But if you find the derivative of this function, this new function that you got, it should match up with what you have in your antiderivative here, your integral. So I just want to point that out. It's an easy way to check. It keeps derivatives fresh in your head. All right, let's get on with these other examples. All right, on this slide, a couple more examples you can see here. We have example 5 and example 6. Example 5. This should be pretty reminiscent of seeing one term in a denominator when you were finding derivatives. Well, guess what? We have to do it again here for antiderivatives. We can separate this into 3 different fractions. So let's do it. So I rewrote the square root of x as x to the 1/2, and then I more or less distributed this x to the 1/2 to each term in the numerator. Boom, boom, boom. So now we can simplify these. X squared divided by x to the 1/2 power leaves you with x to the 3/2 power plus 2x to the 1/2 power, 1 minus 1/2. And if we bump this up, it becomes minus x to the negative 1/2 power dx. So we're trying to find the antiderivative of all of this with respect to x. All right. Next step, we can jump right into the antiderivative. Since we have all of these variables with exponents, and they're not in a denominator, we can jump right into the antiderivative. Let's do it. This will be add 1 to the exponent. This is 5/2. Multiply by the reciprocal of the new exponent. Plus 2 times add 1 to the exponent, x to the 3/2. Multiply by the reciprocal of the new exponent. Minus, let's see, add 1 to the exponent, so it'd be x to the 1/2. Multiply by the reciprocal of that exponent. It would be, oh yeah, I guess the reciprocal would be 2 here, huh? Plus c. Sorry, number 6, we're running into your territory. Let me see. There we go. Plus c. Now all we have to do is simplify any numbers that we have left over. Luckily, the first term just stays 2/5 x to the 5/2. This one, though, the second term, we can multiply 2 times 2 and get 4 over 3 x to the 3/2. So 4 over 3 x to the 3/2 minus 2x to the 1/2 plus c. All right, and there's no reason to try to combine these back into one term like we started with. This was just one term. Having these separated out like this is totally fine. All right, next example. We have trig. Oh, fun. All right. So this is more or less a memorize situation. If we're trying to find the antiderivative of a cosine of y, and then subtract the antiderivative of a cosecant squared of y with respect to y, we just have to think of, more or less, what function would give you a derivative that would be cosine of y. Well, that would be sine of y. For the next one, we're going to subtract. What function would give you a derivative that would be cosecant squared y? Well, let's see here. It was cotangent. Cotangent gives you a derivative of cosecant squared. Yeah, but there's also this negative. So if you go back and look a few slides ago, the antiderivative of cosecant squared is negative cotangent. So this would be negative cotangent of y, and then of course our plus c. So the only simplification we have here would be sine of y plus cotangent of y plus c. But again, think of this. What's the derivative of sine? Cosine. What's the derivative of cotangent of y? Well, remember when we were taking derivatives, the derivative of any co-function would give us something negative, and the derivative of cotangent would give us cosecant squared y. So negative cosecant, yeah, this matches up really well with our function that we were trying to find an antiderivative for. All right. I think I have one more example on the next slide, and then we can jump over into the next topic. All right, last example. I made it a relatively simple one for everybody out there, but wanted to make sure I really hit this point. pretty hard here. We cannot use a power rule here yet because we're not allowed to have the variable in the denominator of a fraction. So again, we can move this up to the numerator as long as we make the exponent negative. So from here, we can now use the power rule, which states we add 1 to the exponent and multiply by the reciprocal of that new exponent. The reciprocal of negative 3 is negative 1 over 3 plus c. All right, let's move on to initial condition problems. Just kidding, everybody. I realized just right now that there's no way I'm going to let this slide. There's no way that negative 3 should be there. It should be 1 over 3x to the third power with a negative in front plus c. This is the real answer. We have to bump this down. This whole thing down to the bottom of the 1/3. All right, now let's take a look at initial condition problems. As promised, initial condition problems. You'll be given a first or second derivative and some initial conditions. This is why we call them initial condition problems. Go figure. So the process for solving initial condition problems is basically you're given a derivative, a first derivative or a second derivative. In this case, let's just think about the first derivative, and you find the antiderivative. When you do that, you will end up getting the original function. Almost. If you get some extra information about the function, the original function, then you can solve for c. So we will have to have a plus c to begin with, but then we can use the extra information we have to actually solve for c. And if you are given a second derivative, you have to repeat steps 1 and 2 until you get to the original function, aka no derivatives. You'll see in the examples. The last step then is to write down the function with a value substituted for c. Let's take a look. All right, let's take a look at example 1. I think it's easier for you to see now what I was trying to get across on the last slide. You are given a derivative and then some information about the original function. Notice there's no prime here. This is dealing with h of p, the original function. If we find an antiderivative, that means we take 1 prime away. So let's take a look here. If I know h prime of p equals 10p minus 12p squared, and I want to find the antiderivative of both sides with respect to p, that would look something like this. We are going to take the antiderivative of both sides with respect to p, which means that the left side becomes h of p. An antiderivative and a derivative are inverse operations, so this antiderivative will get rid of the derivative and just give us the original function. On the right-hand side, we can say we've got 10p squared times 1/2, which is the reciprocal of that new exponent, minus 12 times 1/3 p to the third power plus c. So again, I'm going to simplify this and get h of p equals 5p squared minus 4p cubed, all plus c. Cool. Now, how do we solve for c? we can substitute 3 in for p, right? That's what happens if I try to make this h of 3. So let's do that. There we go. And what this means is when I substitute 3 in for p as I did, this entire expression here should equal 2. So now we have 5 times 3 squared minus 4 times 3 cubed plus c equals 2. I think we should be able to solve this. So we're solving this equation right here. So what is that? 5 times 3 squared. 3 squared is 9 times 5 is 45. 4 times 3 cubed. 3 cubed is 27. 27 times 4 is 108. Plus c equals 2. I can combine these to give me negative 63 plus c equals 2. I get that c equals 65. Cool. What's my final answer? Well, once we get our c value, we have to take it and substitute it back into c right there. There we go. So our original function now is going to be h of p equals 5p squared minus 4p cubed plus 65. And there is the final answer for example 1. For example 2, I'm just now realizing I will have to work out half of it on this slide and then other half of this problem on the next slide. So let's start in f double prime of y equals sine of y. So if we start here, we just start with our function. We know f double prime of y equals sine of y. We have to find the antiderivative with respect to y. Remember, you just want to find out what variable is being used. In this case, it's y. Over here, it was p, so I knew it was with respect to p. Here, I know it's with respect to y because that's the variable we're using. So when we find the antiderivative of the left side, we get f prime of y. We can only take away one prime at a time. So this would be negative cosine of y plus c. And you can see here that we have been given some information about the first derivative. So we have to use that first. All right, how do we do this? Well, we can substitute 0 in for all of the y's, which would look something like this. F prime of 0 equals negative cosine of 0 plus c. And when we substitute 0 in for all of the y's, we know we should get a 1 on the other side of the equal sign. Let's see here. So that should equal 1. So we're solving this equation here. Cosine of 0 is 1. So this ends up being negative 1 plus c equals 1, which means then that c equals 2. What do we do with that 2? Well, we have to take it and substitute it back into the first derivative. So now our first derivative looks something like this. F prime of y equals negative cosine of y plus 2. Now on the next slide, I will make sure to have the first derivative and the other initial condition here. Notice this is for the original function, no primes. So we will continue this example on the next slide. Okay, so here is the first derivative with the correct c value from the last slide and the initial condition for the original function. So again, we will take the antiderivative of both sides with respect to y. So all of this with respect to y. And again, we get to basically remove a prime. So we will have f of y equals negative sine of y plus 2y plus c. Now, let's see here. And we set this up very similarly to the last one. We know we will have f of 0 equals negative sine of 0 plus 2 times 0 plus c, and that will equal 6. Because when you substitute 0 in for y, you should get an answer of 6. So I substituted 0 in for all the y's, plus c equals 6. The sine of 0 is 0. 2 times 0 is 0, plus c equals 6. So that just tells us that c equals 6. We take that value, we substitute it back into c for the original function, and we get our final answer, f of y equals negative sine of y plus 2y plus 6. And here's what the original function is. Yay, everybody's favorite physics. All right, remember this. We would have a position function, s of t, and we could find the velocity function if we took the derivative of the position function. And we could also find the acceleration function if we took the derivative of the velocity function. Or if we thought of it like the second derivative of the position function, that would also give us the acceleration. Well, now we can go backward. If we are going to move backward, we do not worry about the second derivative of the position function. And I think the best way to understand what is going on here with this, the velocity function being the antiderivative of the acceleration function, and the position function being the antiderivative of the velocity function, is just looking at these, using what we were using in the last slide. So if I take this equation, a of t equals v prime of t, and I just represent it a little bit differently like this, the antiderivative of a of t with respect to t, and we find the antiderivative of v prime of t with respect to t, then remembering from the last couple examples, if we find the antiderivative of a derivative, their inverse operations, they undo each other. So the right side of this entire equation would become v of t. And the left side, we would just leave it alone. That's how we represent an antiderivative. So you can see where this equation comes from, and you can do something very similar here for the v of t equals s prime of t. Take the antiderivative of both sides and get this one here. But how can we use that to our advantage? I'm so happy you asked. Let's take a look on the next slide. So here we have a function that models the position of a particle at time t. So it says find the acceleration, or find the velocity and acceleration of the particle. So this is something that you're probably pretty familiar with. We just have to find the first derivative, x prime of t, being 3t squared minus 14t plus 15. And then the next one here for the acceleration, you find the derivative of the velocity function, which would be 6t minus 14. So there's that, not too bad. But then we have a second part that you can't see yet. Here it is, find when, important word here, when the particle is moving right. And that just means we're trying to find out where the first derivative is positive. So in order to do that, all we have to do is set the first derivative equal to 0. Then solve for t. Set it equal to 0, solve for t. This factors 3t minus 5 and t minus 3. Cool. So we know that t will equal 5/3 and 3. And these are the critical values. Guess what? We have a little bit of a review here from the last section, or the last unit. So let's see, we know time can't be less than 0. We have 5/3, we have 3. We're just trying to figure out where the velocity is positive, so we pick numbers. So why don't we pick 1, we can pick 2, and we can pick 4. And we have to figure out where is this function positive. Well, let's see, if we put 1 into this derivative here, find x prime of 1, that'll give us something that is positive. So x prime of 1 is positive here. So moving right, x prime of 2, guess what? X prime of 2 will give you something that is negative. That means we're moving left. If we're decreasing, we're moving left. And x prime of 4 will again be positive. So the intervals here would be from, we'll say from 0 to 5/3, and from 3 seconds onward, which we could represent as 3 to infinity. So it's just going to be forever moving to the right after a certain point in time. The last thing that we can do here is we can find the velocity of the particle when its acceleration is 0. So at time, let's see. So I'm going to say it again. We are going to find the velocity when the acceleration is 0. So if we set the acceleration function equal to 0 and solve for t, we can find that the acceleration is in fact going to yield us a value of 7/3 seconds. So if we want to find the velocity at time 7/3 seconds, then we can just substitute this back into the velocity equation here. Now, just using a bit of knowledge that we already have here, you can see that, where am I? Here we go. Since this time is between 5/3 seconds and 3 seconds, we should be having some sort of negative velocity here. And it turns out that if you take this 7/3 seconds and you put it in for this velocity function, you do end up with a negative 4/3 for the velocity. That's just units per second. All right, one more example, then I promise I'm done. Robin Hood shoots an arrow straight upward at 75 feet per second from ground level. How high will the arrow go, and when will it hit the ground? So since we are working with feet units that are imperial measure, we will use the acceleration function, no prime here, just a of t, will equal -32, and that's -32 feet per second, or feet per second squared. This is exactly an initial condition problem. How can we know that? Well, if we take the time to rewrite acceleration as the second derivative of the position function, we can also then write the velocity, an initial condition for the velocity that's sort of hidden up here. This says he shoots the arrow straight up with an initial velocity of 75 feet per second. So we know at time 0, and again, this can be written as s prime of 0, the velocity function. We know that it is 75 feet per second. And even better than that, we know the original function, the original position function at time 0. The arrow is position 0 because it's being shot from ground level. So we can use all of this information to start figuring things out. To figure out the velocity function, we can take the antiderivative of the acceleration function. So remember, if we take the antiderivative of a function with respect to time in this case, and we take the antiderivative of the other side as well with respect to time, we will take one of the primes away, thereby giving us s prime of t and negative 32t plus c. From here, we can solve for t if we have we can use this here. S prime of 0 equals negative 32 times 0 plus c equals 75, right? At time 0, the velocity is 75. So now we can easily tell that c is 75. All right, so how high will the arrow go? Well, I don't think we can answer that yet. When will it hit the ground? I don't think we can answer that yet either. All right, let's then take our new velocity function here. So we have got s prime of t equals negative 32t plus 75. And we can now, what can we do? We can take the antiderivative of both sides with respect to t. So dt equals antiderivative of all of this dt. Let's see. So that gives us then the position function, s of t, which would be negative 16t squared. So I added one to the exponent and divided negative 32 by 2. We can say plus 75t plus c. So here's a nice little secret. When you have a 0 for an initial condition, for both coordinates, so the time would be 0, the position would be 0, the c will just be 0. So we don't even have to worry about that. So let's see here. Can we answer our questions yet? Let's see. What was our velocity function? I want to write that again. S prime of t was negative 32t plus 75. All right. So the velocity function, if we take the time to set this equal to 0 and solve for t, we get some really weird number, right? We have to start at 0. The only critical value we will end up with is 75 over 32 seconds, which is 2.34375 seconds. out to a few decimal places. That may actually be exact right off the top of my head, no big deal. But if you select a value between 0 and 2.5, say 1, and you select a value after that, say you select 3, and you put this in the velocity function that we have right here, you'll start noticing that the velocity is increasing here. It's positive, and it's decreasing here. It's negative. And that all has to do with like the velocity away from the Earth is positive, and the velocity coming back to the Earth is negative. But at this point, we have a what is this? A relative maximum at that particular point. So that means if we take this time and we put it into our position function, we can figure out the height. And you would get 87.89 feet. Let's just go to 2 decimal places. So here, S of 75 over 32 is about 87.89 feet. So it reaches almost 90 feet off the ground. So check, how high will the arrow go? We got that. When will it hit the ground? So this is another question dealing with the position. Again, we're trying to find time, but when it hits the ground, we can say that the position, the height off the ground, is 0. See, at time 0, it started at height 0, and then we have to find the time when it'll hit the ground again. The reason we had to use the velocity function to figure out when it would top out, or when the maximum height will be, is because we know that when the velocity is 0, the function, the arrow is at its highest point. So all we have to do then to find when the arrow will hit the ground is set the position function equal to 0 and solve. We already know 1, and that's going to be t equals 0. And you can see that if you factor out a t, that the t would be 0. So now if you just set this other factor equal to 0, you will see that the time will end up being 75 over 16 seconds. Another, which is about, I'm guessing, 4.68 seconds. And since we had a perfectly balanced arrow shot here from Robin Hood, it started out 0 feet off the ground, it ended up 0 feet off the ground, it topped out at this. You'll notice that this is exactly twice as big as this, so that's just another way to think about it. Hope that helped. Good luck.